So in this video, we're going to introduce a new type of function called a vector field. These are super important for what we're going to be doing the rest of the semester in this class. So it's important to get a good idea of what's going on here. For the most part, we're going to say what they are and then see some graphs of them and see how they're working here. So start off with the definition. So what we're going to have here for a vector field in the plane is this is going to be a function that inputs a point xy and outputs a vector. So note here the capital F here is bolded to indicate that this is a vector. And so for each x and y, we get a little f of xy I plus gxy j for some functions little f and g here. So for example, a very easy vector field here would be just whatever we input for x and y, we go in the x units in the I direction and y units in the j direction. So for example, the vector field f evaluated at 1, 2 would be just I plus 2j. So vector fields, as I said, are super important. They're going to show up in lots of applications. For instance, anything you're doing in physics that uses a force, the force is going to give you a vector field because at each point, your force could be different and gives you a vector at that point. So let's look at an example here. So let's continue with our vector field xi plus yj. So for example, we can continue to evaluate this at some point. So if we evaluate at the point 1, 1, we just get I plus j. If we evaluate it at 1 and 1/2, we get I plus 1/2 j, etc. for any other points you'd like to put in. Now, we represent these vector fields geometrically, so what we do is we go to the point xy, and then we graph the vector f of xy at that point xy. And of course, since we can plug in any xy, this would mean there'd be a vector at every single point in the domain of boldface f here. But what we do is we just graph a representative sample of the vectors so that we can actually see what's going on. So let's just start with seeing what a couple of these vectors look like. So f of 1, 1 was just I plus j. So note we start this at the point 1, 1 because that was our input. 1, 1 was our input. And then we draw the vector I plus j. So we go 1 unit in the I direction, in the x direction, and 1 unit in the j direction to get that vector. And similarly, here we have f of 1, 1/2. So remember this is I plus 1/2 j. So we start 1 unit in the x direction for the 1 and 1/2 unit in the y direction for the 1/2, and then we graph the vector I plus 1/2 j starting at that point. And we can continue to do this and use this to kind of fill up the plane with enough vectors to see what's going on. But of course, graphing a lot of these by hand becomes kind of a pain, so the best thing to do is use a computer to help with this. So we use Mathematica here to plot our vector field, and I will include the worksheet for the Mathematica so you can go ahead and play around with vector fields yourself with this. But here we see for our vector field xi plus yj, the vectors are all just pointing away from the origin. And the further away from the origin you get, the longer the vectors are. So it's not super apparent here, but you can see this vector here is smaller than this vector out here. But one nice thing we can do with Mathematica to help us out with this is we can get a color coding. Notice these vectors are different colors. Those different colors correspond to different lengths of the vectors. So we can go ahead and add this on to our graph here. So we can see as we get darker in the purple, they're smaller. Whereas we get this, say up here, this orangish color, up in here, these are about 6 units in length. So those vectors, if you took the magnitude of f of x, y at that point, it would be about 6. So that can be a helpful tool in Mathematica to get an idea of exactly how long those vectors actually are. So let's look at a few other vector fields to kind of get an idea of what they're going to look like and what's going on here. So if we just take the vector field f of xy equals 2i, that means at every point xy, we're just associating the vector 2i. So that vector field just looks like this. Everything is the same length. They're all length 2, and they're all pointing in the I direction, no matter where we are. So one thing you can think of when you're thinking of vector fields, you can think of these as force fields. You can also think of them as like flowing water. So what this would be saying is if I dropped something, say, in here, this vector field would push it in this direction straight along here. Whereas in the previous one, if I drop a particle somewhere, it's going to push it out in this direction. So we can think of these almost as like flows. So here's another vector field. So in this case, everything is going to point in the I direction, but the length of the vector is going to change with our x since the vector field is xi. So the further we go in the positive x direction, the larger our vector from our vector field will be. And further in the negative direction, the larger the vector magnitude will be. It'll just be pointing in the negative direction. So we can see that here, the further right we go, the larger we're getting. And notice when we look at along the x-axis here, we're just getting the 0 vector, so nothing's going, or along the y-axis, you're getting the 0 vector here, so nothing's going on at that point. So this is another interesting vector field. So our very first vector field was kind of everything flowing away from the origin. This vector, where we take negative yi plus xj, we can see this one is just kind of swirling around the origin. So this curls around the origin. So you can think of this as, it's not quite water going down a drain because it's not ever going towards the origin. It's just spinning around the origin. In this case, the further away from the origin we get, the faster it's spinning. Here's one more interesting vector field. So if we do x plus y, I plus y minus xj, we can see this one kind of spirals away from the origin. So it starts off, and think of the flow lines kind of going like this, and they're gradually turning around. So this is going to spiral away from the origin as we move away along any of these vector fields. We can also define vector fields in 3 space. So in this case, we just have 3 functions to go with our I, j, and k, and our inputs are x, y's, and z's. So for each point x, y, z, we get a vector. Now these are going to be a little bit harder to graph by hand, of course, because everything is harder to graph in 3 space by hand. But even with technology, it can often be a little bit difficult to kind of see what's going on. But let's look at a couple of them just to get an idea. So we saw in our first example, xi plus yj was just kind of spreading out from the origin. So if we include on here the same type of vector field, but we include the z direction as well, we again get a vector field that's just kind of pointing out and spreading out from the origin. Now, if you look at the Mathematica worksheet with this, you can go ahead and grab the picture of these vector fields with the mouse and rotate it around so you can get a better idea of kind of what it looks like from each direction. But here we just get everything pointing out from the origin, and you can see the vectors are changing color, so the further away, the larger the vectors are getting. And let's look at one more example. So we take the vector field we had before, the minus yi plus xj, which was spinning around the origin, and now we add plus zk to this. And we can see, this is a little bit messy to see, but basically we're spinning around the z-axis. But since we have that zk, the larger the z gets, the more the vectors are pointing upwards. So when z is equal to 0, this is still just rotating around the z-axis and not going up or down. But as you take a positive z, they start spinning like upwards in kind of a spiral around the z-axis. And when your z is negative, they spin down. And we can change our viewpoint on this to see if we look from above, we can kind of see that spinning around the z-axis of this vector field. So we're going to encounter vector fields a lot. It is a good idea to take that Mathematica worksheet and just type some vector fields in and kind of play around with them to see what different vector fields look like to get a feel for them. We don't always have to use technology. We can, of course, graph them by hand by just picking a bunch of different points and graphing those vectors at the point. So it can be done by hand. It's just more efficient to use a computer to do this.